So today we're going to deal with similarity, especially as it relates to pumps. A lot of these pump parameters, like we saw in the last lesson, the pump curves are determined experimentally. So because they're determined experimentally, dimensional analysis and similarity come in quite handy. So primary variables of interest when we deal with pumps are the head rise HA, the shaft power omega or W dot shaft, and the efficiency eta. So those are things we're trying to find. The variables that those things might depend on, characteristic diameter, so basically the impeller diameter for my pump, some sort of length that could be associated with the length of the piping system that I'm trying to pump this stuff through, surface roughness, again, relative to those pipes, the flow rate going through the pipes and pump, rotational speed of my pump, as well as the fluid properties, fluid viscosity, and fluid density. So I expect these three things I care about depend on all those things down there. So grand total, I had 10 variables written down on the board, 3 dimensions of length, mass, and time. If you remember from dimensional analysis, Buckingham pi theorem, I take my 10 variables minus 3 dimensions, gives me 7 dimensionless variable combinations or pi groups for this problem. Those 7 could be these ones I've written down here. So some length over d, some epsilon over d, rho omega d squared over mu. This is basically like the Reynolds number, rotational speed times diameter, or usually times radius, times omega gives me a velocity. So basically one of these is a velocity, then I still have a diameter there, so that's basically Reynolds number. Q over omega d cubed is my last one up there, and then 3 of these have a special name. So along with the head coefficient, CH, is G times HA over omega squared d squared. The power coefficient, C power, is W dot shaft over density, omega cubed d to the 5th. And efficiency, eta, is rho GQHA divided by W dot shaft. So again, power coming out, or power transferred to my fluid, rho GQHA, that's the same thing as gamma QH. You might remember that as the power transferred to the fluid. And W dot shaft, power input. So efficiency as usual, power out divided by power in. So again, those are 3 things I cared about: head, power, and efficiency. So those are going to be how I calculate those guys. Now in terms of the 7 dimensionless groups wrote on the board, not all of them are actually that important in terms of this pump flow. So one thing is that the Reynolds number, again represented by this rho omega d squared over mu, is generally fairly high. Because it's fairly high, it generally doesn't change the other parameters very much. So we saw that way back when we dealt with similarity for right after dimensional analysis. We saw in certain situations that the Reynolds number was higher than roughly 1,000 or 10,000. Things like CP didn't change, the pressure coefficient. Same thing happens here. So high Reynolds number doesn't actually change these other variables that we care about, so I'm not going to worry about that guy. Surface roughness is generally small, so epsilon over d, don't really worry about that guy either. Length over diameter, again, that's really only there to calculate the head loss of my system, so don't really worry about that guy. The only one that actually really matters in terms of that top group is this guy, Q over omega d cubed. And so because that's the only one that actually changes anything, I can write all my variables of interest. So my head coefficient is some function of that particular pi group. My power coefficient is some function of that particular pi group, and my efficiency is some function of that particular pi group. So that's really the only guy that actually influences and makes any of these actually change. So as mentioned, for similarity purposes, the only variable I really care about is this combination Q over omega d cubed. So because he's the important one, he gets a special name, CQ, which is called the flow coefficient. And so that way, if this guy has the same value, so I can go in and I can change omega d and q to some different values, but as long as I have the same value overall, my values for CH, C power, and efficiency will all have the same value as well. And so for similarity purposes, as long as my CQ remains constant, my CH will be the same, C power will be the same, and efficiency will be the same for geometrically similar pumps. What this allows is when you do tests or experiments for one single pump, you can then scale the results to other pumps of the same family. So if I have the same pump but with just different diameter impellers, so pretty much exactly the same, just different sizes, I only have to do experiments on one of those. Then I can scale the results using the similarity laws like we saw about a month ago. We can get another dimensionless parameter that's useful by playing with some of these other dimensionless variables. So you may remember from when we did dimensional analysis, all these variables aren't unique. I can make some out of others by multiplying them, dividing them, doing whatever else I need. So this guy's not necessarily an independent one, because they don't depend on the two that I'm going to use here. So I'm going to take the square root of the flow coefficient and divide it by the head coefficient to the 3/4 power. That's going to get rid of diameter. And so flow coefficient Q over omega d cubed, square root of that, head coefficient G HA over omega squared d squared to the 3/4 power. Diameters cancel out. What I'm left with is omega times the square root of Q divided by GH to the 3/4 power. And that I'm going to call NS. And NS represents something called the specific speed. So a low specific speed corresponds to a low flow rate and or a large head rise. You can see from the equation, flow rate on top, head rise on the bottom. This is a situation for most centrifugal pumps. Most centrifugal pumps operate with low flow rates and large heads. If you have a high specific speed, that corresponds to a large flow rate and or a small head. That's where axial flow pumps operate. We'll see that. See those next lesson. Now, in the US, instead of using that dimensionless version that we just saw, there's a modified dimensional form of the specific speed using common US units, not necessarily standard units, but the common ones used for pumps. So for example, omega, instead of being in radians per second like it should be in the other version, is now in RPMs. Flow rate Q, instead of being in either feet cubed per second or meters cubed per second, is now in gallons per minute. And then my head rise is still in standard units of feet, but notice that my G is completely gone as well. Figured for changing these units, might as well just get rid of that too. So this is the dimensional version of specific speed, used a lot in the US. You can actually make all these conversions and figure out that this dimensional version, NSD, is 2,733 times that dimensionless version that we saw on the previous board. So centrifugal pumps, we know, has a relatively small specific speed. In terms of this dimensional value of specific speed, centrifugal pumps are generally between 500 and 4,000. Axial flow pumps generally above 9,000. Reason for that is basically their efficiency curves. So we look at efficiency versus specific speed in dimensional form. Centrifugal pumps down in the low numbers, 500 to 4,000. Their peak is somewhere in the neighborhood of 2,000. And so peak efficiency is roughly 2,000. That's going to help, or this range, 500 to 4,000, is a pretty good range to have pretty good efficiency for those pumps. Axial flow pumps, peak efficiency, somewhere around 11, 12,000, somewhere in there. So again, if I'm way up at a high specific speed, it's better to use an axial flow pump. If you're somewhere in the middle, that's where mixed flow pumps come in, and we'll deal with the differences between all these in the next lecture. But again, this should help with pump selection, figure out what the dimensional specific speed you're going to be having in your specific scenario, and then from that you can see whether you should use a centrifugal, axial, or mixed flow pump based on that number.